Invisibility Cloaking, Theory and Experiments. Introduction. The idea of invisibility has fascinated people for millennia, inspiring many myths, novels, and films. Invisibility cloaking has recently become a subject of science and technology. This paper describes the important current theoretical and experimental developments and tries to project into the future. Camouflage. Invisibility may be achieved through three principal methods: camouflage, transparency, and cloaking. Many animals and some plants use camouflage to disguise themselves from predators, for example, by assuming the shapes and colors of objects in their surroundings. The military has long used forms of camouflage. A recent military application of camouflage is stealth technology. Stealth planes have aerodynamically unusual, edgy shapes and are coated with a special material. Both features serve the same purpose: to make the plane invisible to radar. How does it work? In radar, electromagnetic microwaves are emitted by a source, and their reflection by an object, an airplane, for example, is detected. From the direction and the time delay of the reflected waves, the direction and distance of the object are inferred. If the object does not reflect the electromagnetic microwaves back to the source, it will not appear on the radar. This is precisely what stealth technology achieves. Owing to the edgy shape of the stealth plane, most of the incident electromagnetic waves are reflected in different directions. The coating of the plane absorbs the rest. In this way, the stealth plane has become completely black in the spectral range of radar. As for radar waves, the sky is black, not blue, and the plane has assumed the color of the background. The stealth plane is camouflaged. Another recent example of camouflage is optical camouflage, developed by the University of Tokyo's Tachi Laboratory. Figure 2 shows an example of optical camouflage. A camera captures the background scene behind the person. The image is processed and projected onto the person via a semi-transparent mirror. The person wears an invisibility cloak made of a retroreflective material that reflects light back in the direction whence it came, like cat's eye reflectors do. As the cloak carries the projected image of the background, the person seems to disappear, but surely the equipment standing around the person is clearly visible. In addition, optical camouflage works only in one direction: seen from the side, the person is visible. Nevertheless, optical camouflage may become a useful tool in some situations where obstacles are in the way of sight, for example in surgery, where the surgeon's hands and instruments may obstruct the view. Figure 3 shows how optical camouflage works. Transparency. H. G. Wells's novel The Invisible Man represents another strategy for becoming invisible: transparency. In Wells's novel, The Invisible Man, a disgruntled college professor invents a substance that somehow changes the refractive index of his body. Most transparent substances, like glass, air, or water, modify the speed of light, because the atoms or molecules of these substances absorb and re-emit light, which takes time. The delay caused by the atoms and molecules results in a reduced speed of light and hence in a refractive index larger than 1. It is, however, also possible to achieve a refractive index smaller than 1, although only in narrow bands of the spectrum. In these cases, the atoms or molecules advance the wave fronts of light because they are excited such that their electron clouds oscillate ahead of the light. If the refractive index is uniform in a material, light is reflected and refracted at the boundary but otherwise is traveling straight through. On the other hand, if the refractive index varies, light is scattered at the index inhomogeneities and gets lost. Most white substances appear white because of such scattering. Milk, for example, consists of minuscule oily droplets, fat, in water. The refractive index of the droplets differs from water, and hence light is scattered at them. It does not penetrate the substance, and the diffused light appears as white. Now, human bodies are visible, because they absorb light. Most of the absorption is due to the scattering of light in biological tissue, in the cells of which the bodies are made. If the refractive indices of a person's cells could somehow be changed to the refractive index of air, the person would become transparent and disappear from view, like the invisible man. Some animals, for example, some jellyfish, are transparent, but the cells of higher order animals are usually much too complex and diverse for transparency to become a serious option for disguise. Exceptions are the transparent parts of the body, most notably eye lenses, which consist of uniform cells kept in a state between life and death. If this balance is upset, the lenses become opaque as a cataract develops. Transparency is the idea behind some proposed forms of invisibility by technology. For example, in plasmonic covering, a particle should be surrounded by layers made of metals and transparent substances, such as glass. The layers are designed such that they cancel the scattering of light at the particle, hence making both the particle and the layers transparent, that is, invisible. Another proposal exploits the resonance of the particle with a negative refractive material that cancels out scattering. In a material with negative refraction, the wave fronts of light appear to move in the opposite direction from the propagation. The clearest and most advanced form of this concept is the complementary media invisibility cloak. 3 Here, an optical anti-object is placed beside the object one wishes to make disappear. The anti-object should be made of a negatively refractive material that exactly compensates the optical appearance of the object. An image is contained in the deformations of light wave fronts caused by the imaged object. If these deformations are reversed, the image disappears, and the object becomes transparent, that is, invisible. The optical anti-object must be tailored to the object and placed precisely at the correct distance, that is, the distance where it is made to cancel the image of the object. The more complex the object is, the more complex the anti-object must be for reversing all the scatterings of light. Such cloaking at the distance cannot be instantaneous, as the light scattered by both object and anti-object must settle to a stationary state where it becomes synchronized. A stationary light field has only one color. So, in practice, these forms of transparency will work only for small objects and for small parts of the spectrum and not for large objects in many colors. Cloaking. Cloaking is a universal strategy for invisibility that works for objects of arbitrary compositions and shapes within a given size. In cloaking, the hidden object is enclosed by the cloaking device, a transparent shell that guides light around the object as if the light would propagate through empty space. In this way, both the interior of the cloaking device is hidden and the act of hiding is concealed. How does one find the right design for such a cloaking device? As the Invisible Man symbolizes transparency as a strategy for invisibility, inspiration for cloaking may come from the Invisible Woman, a cartoon figure from the Fantastic Four. The Invisible Woman is said to create a mysterious force field around her that bends space. Light follows the curved space such that it smoothly flows around the Invisible Woman, like water in a stream flowing around an obstacle. The key idea here is the concept of curved space used for invisibility. The idea that turns the Invisible Woman with her fabled force field from a fictitious character into something close to reality is the insight that no force field is needed, that light-refracting materials like glass or water appear as curved spaces by themselves. This idea comes from Fermat's principle of the shortest optical path. Suppose that light travels from A to B according to Fermat's principle, light follows the path that takes the shortest time. In refractive materials, the speed of light is modified, in most cases reduced, by the refractive index. The time it takes for light to pass through an infinitesimal element of space is proportional to the refractive index. So, light index varies in an optical material or in the boundaries between materials, the optical measure of path length varies, which is the defining feature of a curved geometry. To provide a simple example, a lens focuses parallel light rays into a point, the parallels meet there, which is the hallmark of a non-Euclidean geometry. So something as familiar as a lens creates something as fantastic as a curved geometry. The bending of light in materials or, equivalently, the change of the spatial geometry by optical materials is the cause of most optical illusions. For instance, the figure used to illustrate Fermat's principle shows the path of light in a mirage. The air above a hot surface, hot tarmac, or desert sand is hotter than the air farther above. As hot air is thinner than cooler air, the refractive index is lower above the hot surface. Light rays are bent upwards, conjuring up images of water in the distance that, in reality, are images of the sky. Such optical geometries may also be employed for creating the ultimate illusion, invisibility. Imagine an optical material changing the geometry of space. The material acts like a transformation of space. In the device, each point in real space is put to a new location in a virtual space. Outside of the device, space remains the same. The device creates the illusion that light propagates along straight lines through the virtual space, whereas in reality it is bent. Suppose the device encloses a hollow region that is not part of the virtual space or, to be more precise, a region with a surface that, in virtual space, has become a single point. The red circle in Figure 9b is reduced to the red dot in Figure 9a. As the hollow region is not part of the virtual space where light propagates, everything inside it has become invisible. As the coordinates of virtual space smoothly go over into the coordinates of real space at the outer surface of the device, light rays are not distorted. Any object inside the cloaking device is hidden, and so is the act of hiding itself. Moreover, the cloaking device not only would bend light rays but would modify the entire structure of light waves in such a way that detecting the hidden object is impossible. Light waves would advance around the hidden core of the device, engulfing it. This idea of cloaking by coordinate transformations was put forward by two independent groups. Their theories appeared in Science Express on May 25, 2006 and were published back-to-back in Science magazine later on. The first paper 9 only considered isotropic materials, optical materials where the speed of light at each point is the same in each direction but may vary from point to point. Most natural optical materials, except for some crystals and all liquid crystals, are isotropic. In isotropic materials, invisibility is perfect only for light rays, but the cloaking device may cause dislocations of light waves. In addition to the optical implementation of coordinate transformations, some other tricks are required. The second paper degrees considered anisotropic materials for cloaking or other manipulations of electromagnetic waves. Here, perfect invisibility is possible in principle, but not in practice, as is discussed later. In October 2006, the first cloaking device was demonstrated, 11 for microwaves. Science magazine regarded cloaking as one of the top 10 science breakthroughs of the year. It was top in physics and engineering. Scientific American listed the inventors of cloaking devices, Sir John Pendry, David Smith, David Schurig, and Ulf Leonhardt, among the top 50 policy, business, and research leaders of the year. The first paper 19 on cloaking had initially been rejected by most major science and physics journals before it finally appeared in Science, but since 2006, cloaking has become a mainstream subject on which about 1,000 papers have been published so far.